All right, so this is number 25 out of chapter 2.6. In this particular example, they ask you for a few things. We're going to start with finding the domain of this function. So in this particular case, the domain, we're simply looking for values that make our graph not exist. So a good idea for this first one, and we're going to use it a bit later, is to go ahead and factor the denominator. Minus 2x minus 3. Looking at this, the only limiting factor for the input I can tell is going to be when my denominator is equal to 0. So I want to know when this is equal to 0, and I know that that can't be the case. So if I were to factor this out, I'm going to get x minus 3 times x plus 1. And that cannot equal 0. Therefore, x cannot equal 3. And x cannot equal negative 1. Okay? So if I were to write out the domain, I would write that x is the set of all real numbers. X is equal to the set of all real numbers except x cannot equal 3 and x cannot equal negative 1. Okay, so this is the domain of f. And the domain of g, well, that one's a bit simpler. We simply know that x minus 3 cannot equal 0. Therefore, x cannot equal 3. And you can write it out the same way. All right, moving on to b. Well, for b, they say to go ahead and simplify f and find any vertical asymptotes. Okay. As we recalled from the notes, vertical asymptotes happen when our graph does not exist, or in other words, when our denominator is 0. Well, fortunately, we already found that in part A. So we know that vertical asymptotes will happen whenever we have a 0 in the denominator, and we know that happens at x equals 3 and x equals negative 1. So those are my vertical asymptotes. I'm going a little out of order, but that's because I was excited. I already had the information. Okay. Now it did say to go ahead and simplify, so we're going to go ahead and simplify f, and the way we go about that is we're going to simply factor it. So I have f of x is equal to x squared minus 1 over x squared minus 2x minus 3. Okay, so I go ahead and graph this out, and I'm going to get x minus 1 times x plus 1 over, well, I already factored this. I get x minus 3 times x plus 1. Okay, and then I cancel those out, and I get x minus 1 over x minus 3. Now, what they mean by a hole is a hole occurs when at a point where that we canceled out. So this point right here that we canceled, we can't just forget about it. Okay. In this particular case, what we're going to want to do is make sure that we realize that this is still an important point because x, okay, equals or cannot equal negative 1. Therefore, that is a hole. So basically, the idea of a hole is when you cancel, okay, you're losing part of what your value can't be. So in this case, x cannot equal negative 1. And once we simplify, we kind of lose that. So we don't want to lose sight of that piece of our function. Oh, and I apologize. That's actually, that looks like that's part C that we just did. So part C, identifying the hole, what you're basically doing is what you canceled out to simplify, you're identifying that and realizing that that is in fact a hole. Now, for D, they want you to fill in the chart here. Okay, and I'm not going to do the whole chart, but I'll do a piece. And we have X, and then they want from -2, -1, 0, 1, 2, 3, and 4. Okay. Now basically what we're doing with this is we're just trying to get a basic picture of what we're looking at. So this is just for f of x. Oops, probably should have used a ruler. And g of x. Okay. Now f of x at -2, that you would just plug in, and for this particular function you would get 3 over 5. I'm not going to go over this, but you just take you take -2, you plug it in for all of your x's, and you see what the output is. Okay? And for g of x, you would do the same thing, and you would get 3 over 5 as well. Well, I know at -1, well, that's where I have a hole, so that my graph is in fact undefined at that point. Okay. Oh, and going back real quick, if you verify graphically, I apologize, x equals -1 in fact isn't an asymptote. That actually just works out to a hole, which is what we found in C. And I'll clarify in class tomorrow exactly how we can tell the difference between a hole and an asymptote. All right, and so for g of x, we have at -1. Well, at -1, it works out to, you plug it in, you get 1/2. Okay, at 0, we can actually verify that pretty easily. And what's nice about this is once we identify our holes and our asymptotes, we can actually just use the simplified function because everything else will cancel out. So you plug a 0 into here, and we'd see that that's 1 over 3. That cancels, and we get -1 over -3, or 1/3. Okay, going up to our g of x function, hey, we would actually get the same thing there, 1 over 3. If you notice, g of x and the simplified version of f of x are in fact the same, and you're supposed to be noticing that they have a lot of similar characteristics and a lot of different characteristics. So for the rest of these, you can go ahead and plug them in and see where you get, and that would be the conclusion of number 25.